Think about this for a second. How can one tiny particle push another one from across a room with nothing in between? It's just empty space. There's no string, no contact, nothing. Well, physicists came up with an absolutely brilliant way to think about this, a concept they called the electric field. And that's what we're diving into. So here's the game plan. We're going to start with that core mystery, that invisible influence. Then we'll see how scientists figured out a way to actually describe and map this thing. From there, we'll look at what happens when you combine fields, go from tiny points to big shapes, and then we get to the really weird stuff. We're talking about infinity. All right, so first up, let's tackle the thing that really had early physicists scratching their heads, this whole idea of action at a distance. Yeah, this is the question, right? You've got two positive charges, they push each other away. We know this. But how? How does one charge even know the other one exists? What's happening in that empty space between them? And this isn't just some deep thought for a late night. It's a huge practical problem if you're trying to actually calculate anything. Just imagine this, okay? You've got a bunch of charges set up, and you want to figure out the force at some random point in space. So you drop a little test charge there, and you do all the math. Great. But what if you want to know the force on a different test charge? Well, you got to start all over. Every single time. It's just so repetitive. You just know there's got to be a better way to do this. And of course, there is a better way, and it's called the electric field. See, the big idea was to stop thinking about the force between two specific charges and start thinking about the space itself. It's like they decided to create a map, not of a place, but of a potential force. And this is the key. The electric field is something that's created by a charge, and it changes the space all around it. It's there, everywhere, all the time, even if there's no other charge around to actually feel it. We define it as the force that would be felt per unit of charge if you were to put something at that spot. The best way to wrap your head around this is to think about something you already know really well. Gravity, right? We talk about Earth's gravitational field. It's about 9.8 newtons per kilogram. What does that mean? It just means for every single kilogram of stuff you put somewhere, the Earth pulls on it with 9.8 newtons of force. Well, the electric field is literally the same idea, just for charge instead of mass, so its units are newtons per coulomb. So whenever you hear a physicist say the word field, all they mean is some quantity that has a value at every point in space. It's like a giant invisible spreadsheet laid over the universe. For example, think about the temperature in a room. Every single point has a temperature value, right? But it doesn't have a direction. That's a scalar field. The electric field, though, is a vector field. That means at every single point in space, it has not just a strength or magnitude, but also a direction. It's pointing somewhere. And figuring out that direction? Super simple. It's all based on a rule we just decided on. By convention, the direction of the electric field is simply the direction a positive charge would get pushed. So, if you have a positive source charge, the field lines point away from it. And if you have a negative source, they point right towards it. Easy as that. Okay, that's all great for one charge, but the universe is full of charges. So what happens when you've got a whole bunch of them all creating their own fields? Well, this is where physics gives us a beautiful, simple gift. It's called the superposition principle. And I know, it sounds super complicated, but it's actually the opposite. All it means is that if you want to find the total field at some point, you can just pretend only one charge exists, calculate its field. Then pretend only the second charge exists, calculate its field, and so on. Then you just add all those individual field vectors together. That's it. It's that simple. And you can see it perfectly here. Take a look at that point P. You can see how each charge, Q1, Q2, Q3, is creating its own little field vector pointing away or towards P. The net electric field, that big vector E, is just what you get when you add all those little arrows together tip to tail. It's just so elegant, you know? The universe works in these beautifully simple ways. And this whole superposition thing becomes a total lifesaver when you've got symmetry. Check this out. We have two identical positive charges, and we're looking at a point P right in the middle, but a little bit above. Okay, so the charge on the left pushes P up and to the right. The charge on the right pushes P up and to the left. See what's happening? The to the right part and the to the left part are exactly equal and opposite. They just cancel out. Poof! All you're left with is the up part from both. It simplifies the problem like you wouldn't believe. All right, so we've got point charges down. But let's be real, most things aren't just a handful of points. What about a charged up metal rod or a flat plate? Things where the charges spread out smoothly. It's time to go from points to actual shapes. Yes, so far it's all been about discrete charges, individual points you can count. But now we're talking about continuous distributions. Think of it like charge being painted or smeared across a line or a surface, or even through an entire volume. So, how in the world do we deal with that? Well, the strategy is one of the most brilliant tricks in all of physics and math. It's the whole idea behind calculus. You take your big, complicated shape, and you mentally slice it up into a gazillion tiny little pieces. So tiny, you can treat each one as a point charge. Then you find the field from one tiny piece, and the next, and the next. And then you just add them all up, an infinite sum for an infinite number of pieces. And this trick works for anything. You can have charge spread along a 1D line, like a wire, or across a 2D surface, like a sheet of paper, or even throughout a 3D volume, like a plastic ball. It doesn't matter. The method is the same. Chop it up, find the piece's contribution, and add them all together. Now, this is where things get really, really weird. Because when you take this powerful technique and apply it to objects that are, well, infinitely big, you get some results that just seem to break your brain. Okay, surprise number one. Remember how the field from a single point charge drops off with the square of the distance? The inverse square law. Well, for an infinite line of charge, the field still gets weaker as you move away, but it does it much more slowly. It only drops off with distance, not distance squared. But that's nothing compared to the infinite plane of charge. Just look at the field here between these two plates. It's completely uniform. I mean, look at those lines. They are perfectly straight, perfectly parallel, perfectly evenly spaced. That means the field has the exact same strength and direction everywhere. And here it is, the big, mind-bending conclusion. For an infinite plane of charge, the electric field does not get weaker with distance. At all. It is constant. Think about that. Whether you're 1 tiny millimeter away from it or an entire light year away, the strength of the field is exactly the same. How wild is that? And why? The reason is actually kind of simple when you think about it. If a plane is truly infinite, no matter how far you back away from it, it still looks exactly the same. It still stretches out forever and every direction. There are no edges to give you a sense of scale. Your perspective just doesn't change. And if the plane looks the same, the field it creates stays the same too. So this brings us to maybe the biggest takeaway of all. The electric field isn't just some math trick we invented to make calculations easier. It's not just a clever shortcut. It is a real physical entity. When you put a charge somewhere, it fundamentally changes the space around it. It creates this field. And that field is what tells the rest of the universe, hey, I'm here. So we started out with a simple question about an invisible force, and we ended up uncovering this fundamental entity that fills all of space, a real thing that's woven into the very fabric of reality. It really makes you wonder, doesn't it? What else is out there, hiding in plain sight, shaping our universe in ways we haven't even begun to understand?